We're in Chapter 10, Section 3 of Barnett. We're looking at continuity, a very famous topic and very popular one. And our goals for this section are to understand what continuity is, how to apply continuity properties, that's going to be the second thing. And finally, we're going to look at we're going to be looking at a way to solve inequalities using continuity properties. Okay, we're going to look at a method called sign charts that is going to enable us to solve these inequalities. Okay, well, as we've seen so far, some graphs have holes in them, some have breaks, and others have all kinds of irregularities. So what we want to do is study each one of these out of in this section. Then, through the study of limits, we'll extend this further and examine what's called an instantaneous rate of change in the next section. Okay, so more of that later. Well, the basic definition of continuity is given here. That's really the one thing you should get out of this section, is what it means for a function to be continuous at a point. Well, a function f is continuous to the point x equals to c. Okay, we oftentimes say at a number or at a point. So you might see it written this way somewhere else. F is continuous at a number, x equals to c, if the limit as x approaches c of f of x exists, 2, f of c exists, and 3, those two things, the limit and f of c, are equal to each other. So very basic. Those three conditions need to be satisfied for f to be continuous at a point x equals to c. If one of them fails, the function is not continuous at that point. So a function f is continuous then on an open interval, extending this further, a comma b, if it is continuous at each point on the interval a to b. Okay, now, as you can imagine, if a function is not continuous, we say that it is discontinuous. Okay, so why don't we take a look at an example. How can we tell if f of x equals x minus 1 is continuous at x equals to 2? Is this function continuous at x equal to 2? Well, we check for our three conditions. First of all, does the limit at 2 exist? The answer is yes, because the limit as x approaches 2 of x minus 1 is just 2 minus 1 or 1, right? Since this is a polynomial, the limit must exist. Second condition, is f of 2 defined? The answer is yes. When you plug in 2, you get 2 minus 1 or 1, so f of 2 is defined. And the third condition is that the limit, which is 1, equals the function value at that point, which is also 1. So that condition is satisfied as well. Therefore, the function is continuous at x equals to 2. Obviously, you knew this is just a straight line, right? If you were to graph it, this is just the straight line x minus 1 equals f of x, right? And at 2, we get the point 1. Okay, how about this example? Is f of x equal to x squared minus 9 over x plus 3 continuous at x equals to negative 3? Once again, we have to go through our three conditions. Notice the limit at x equals to negative 3 exists. Okay, how do we do this? We use some algebraic manipulation. I'll do it for you here. We factor the top and bottom. This is the difference of squares, the top. And the bottom is well already factored. Cancel out the common terms, and that allowed us to evaluate the limit. And the limit happened to be negative 3 minus 3, or negative 6. Okay, so the limit exists. Alright, but notice the problem we run into is condition 2 fails. Why? Because f of negative 3 is undefined. If you plug in negative 3, the denominator becomes 0. That's a problem. So since one of the conditions fails, this function is not continuous at x equals to negative 3. If you graph this on your calculator, depending on what model you have, some models will actually display a little hole, a little open circle at negative 3. Others will not, but if you were to use the trace key, you'll see that you will not get anything at negative 3. It will just say y equals blank. Okay, now if we were to look at another example here, f of x equals absolute value of x over x at x equal to 0 and at x equal to 1. Well, what is it to happen with this function? Is the function continuous? Let's see. Here's a graph of the function. F of x equals absolute value of x over x. Let me show you how to get this on your graphing calculator, by the way. Here's how to graph absolute value of x over x on your graphing calculator. You go into the y equals editor, and then to do absolute value of x, select Math, scroll over one tab to NUM, which stands for numbers. The first option says ABS or apps. That means absolute value. Hit enter, then hit X, and close the parentheses. That means the absolute value of x. Now let's divide that by x. Let's hit zoom, and option 4, zoom decimal. And here's the graph of absolute value of x over x. Going back to our slides, that's what we have here. And again, on some calculators, the calculator will actually display this open circle. Depends on what version you have. And that's the first problem we run into. Notice, f of 0 is undefined. At 0, this function is undefined because you get 0 over 0, and that's undefined. Not only that, the limit itself does not exist because the limit from the left is -1. The limit from the right is +1. So the limit at 0 does not exist. So both conditions 1 and 2 fail. Obviously, condition 3 fails. We just need 1 to fail, so we know the function is not continuous at 0. On the other hand, notice the function is continuous at 1. Why? Because at 1, the limit from the left and the limit from the right are the same. They're 1. The function value is also 1. The two are equal to each other, so conditions 1 to 3 are satisfied. 1 to 3 are satisfied. Therefore, the function is continuous there. So, as another added bonus here, if two functions are continuous on the same interval, then their sum, difference, product, and quotient are continuous on the same interval, except for values of x that make the denominator 0. Keep that in mind. That's an important property of continuity. Okay, so with that in mind, some continuous functions here. Examples of those would be constant function, right? That's continuous for all x. Think of like f of x equals to 2. That's a constant function. If we were to graph it, here's 2. That's what it would look like. And that's always continuous because it's just a horizontal line. For an integer power n bigger than 0, x to the power of n is continuous for all x. Think of your parabola, think of your cube, x to the 4th, etc., etc. This will just be a polynomial, and it's continuous for all x. Well, speaking of, a polynomial function is continuous for all x. You've already seen that fact illustrated in the notes before. Likewise, a rational function is continuous for all x, except those values that make the denominator 0. So a rational function will always be continuous, except for possible values that make the denominator 0. For n, a not positive integer, the nth root of f of x is continuous wherever f of x, the radicand, is continuous. And for n, an even positive integer, then the nth root of f of x is continuous whenever f of x is continuous and non-negative, right? Because otherwise you would be taking the positive root, the even root rather, of a negative number. Okay, so again, those are the four more common cases for us. Our class focuses entirely on polynomials and rational functions, but these are some nice examples that you should consider.